Why can the sun shine in space without needing oxygen? According to scientists, our sun is currently about 4.6 billion years old, and it has been shining for an incredibly long time that seemed infinite and will continue to do so for about another 5 billion years before it ends. The sun is a star, and we depend on it for our existence. It is the foundation of all life on Earth, providing light and heat that enable photosynthesis in plants, thereby generating oxygen and food. The sun is also crucial for Earth's movements, determining its rotation, maintaining the variations of seasons, and influencing climate. Additionally, the sun affects Earth through solar winds and the phenomenon of solar flares. Solar winds are composed of hot gases emitted from the sun, carrying a strong magnetic field and electric charge. These gases can impact Earth's ionosphere, causing disruptions in wireless communication. Solar flares are eruptions of plasma material from the sun into space. This material can influence Earth's magnetic field and ionosphere, resulting in geomagnetic storms and phenomena such as auroras. So, have you ever wondered why the sun can shine in space, an environment without gravity and without oxygen? The sun's ability to shine is not dependent on the presence of oxygen. The sun's energy comes from nuclear fusion processes that occur in its core. The extreme temperature and pressure at the sun's core cause hydrogen atoms to fuse together to form helium. This fusion releases an enormous amount of energy in the form of light and heat. Unlike a fire that requires oxygen for combustion, the sun's fusion process does not rely on oxygen or any other external element. It is self-sustaining due to the tremendous gravitational pressure that keeps the core hot and dense enough for nuclear fusion to continue. Therefore, the sun's ability to shine is a result of the immense gravitational forces and the internal nuclear fusion reactions occurring within it, rather than the presence of oxygen or any external factors. The reason the sun can continuously shine without needing oxygen is that its process of shining is not based on combustion as we know it, which requires the presence of oxygen. Combustion is a chemical reaction that releases energy in the form of heat, and it occurs when there is oxygen available. During combustion, carbon atoms combine with oxygen to produce carbon dioxide, CO2, and carbon monoxide, CO, while hydrogen atoms combine with oxygen to form water. The burning reactions that we witness on Earth on a daily basis involve the combustion of carbon and require the presence of oxygen to sustain. Once the oxygen is depleted, the carbon burning process ceases. However, the sun's shining is not a chemical combustion reaction as we know it. Instead, it is a form of nuclear fusion reaction. Nuclear fusion reactions do not rely on oxygen. Therefore, the sun does not burn by using oxygen like conventional combustion processes. It can be thought of as a gigantic nuclear fusion reactor, shining brightly for billions of years. In the sun's core, under immense temperature and pressure, hydrogen atoms fuse together to form helium through nuclear fusion. This fusion process releases an enormous amount of energy in the form of light and heat. This energy production sustains the sun's brightness and heat without the need for oxygen. So, while the sun's shining may be conceptually similar to burning, it is actually a nuclear fusion reaction occurring at its core that powers its continuous brightness. In a nuclear fusion reaction, atomic nuclei fuse together to create larger nuclei. The structure and properties of an atom are determined by the nuclei that compose it. Therefore, when the nuclei change, a new element is formed. For example, when two hydrogen nuclei combine, they form a helium nucleus. There are two main forces at play in a nuclear fusion reaction: the electromagnetic force and the nuclear force. These forces determine the behavior and stability of the nuclei involved. This reaction does not require additional materials but rather relies on high temperatures or pressures to overcome the repulsive electromagnetic forces and bring the nuclei close enough to bond and form a new nucleus. For instance, one way to create high temperature and pressure in a nuclear bomb is by detonating other bombs. Another way to generate high temperature and pressure in a nuclear reactor is by introducing electromagnetic waves or supplying high-energy particles. These conditions of high temperature and pressure are necessary to initiate and sustain the nuclear fusion reaction, allowing atomic nuclei to combine and release a tremendous amount of energy. For nuclear fusion reactions occurring in stars like the Sun, the high temperature and pressure are created by an incredibly strong gravitational force. The process of thermonuclear fusion in stars involves the fusion of hydrogen either with itself or with other light elements. Stars with a sufficiently large mass can generate gravitational forces strong enough to initiate nuclear fusion reactions. This reaction generates an immense amount of thermal energy and emits light, such as our current Sun or the stars we observe in the sky. The Sun, for example, has a surface temperature of over 5,000 degrees Celsius and a core temperature of around 16 million degrees Celsius. The pressure in the core reaches up to 25 trillion newtons per square meter. These extreme conditions of temperature and pressure within the stellar core allow hydrogen atoms to overcome their mutual electrostatic repulsion and come close enough for the strong nuclear force to bind them together, releasing an enormous amount of energy. Overall, the process of nuclear fusion in stars, fueled by the immense gravitational forces, is responsible for the tremendous heat and light radiated by celestial bodies like our Sun. Meanwhile, the energy from the stellar burning process will continue to sustain the nuclear fusion reactions of stars until the helium in the core is completely burned and collapses, forming white dwarf stars or triggering a supernova explosion if the star is massive enough. The significance of the Sun in the universe. First and foremost, the Sun is one of the fundamental factors for the existence of life on Earth. The energy of the Sun is formed through the process of nuclear fusion, which continues to occur in the Sun's central region and generates a tremendous amount of energy. This energy radiates from the surface of the Sun in the form of light, providing the necessary energy for life on Earth. The Sun plays a crucial role in maintaining the Earth's temperature, driving weather patterns, and supporting the growth of plants through photosynthesis. Moreover, the Sun's gravitational force influences the motion of celestial bodies, maintains the orbits of planets, and contributes to the stability and dynamics of our solar system. In summary, the Sun's energy production through nuclear fusion not only sustains its own brightness and heat but also provides the essential energy for life on Earth and plays a significant role in the larger cosmic framework. Furthermore, the Sun can also provide essential components necessary for life, such as oxygen and nitrogen. Thus, the Sun is highly important for life on Earth. The activity of the Sun also has an impact on Earth and other celestial bodies. Secondly, the Sun significantly influences planets, moons, and other objects within the asteroid belt of the solar system. The gravitational force of the Sun can affect the orbital motions of planets and satellites. For example, the Moon continuously orbits around the Earth due to the gravitational pull of the Sun. The Sun can also influence the formation and decay of planetary atmospheres. For instance, Mars has lost a significant portion of its atmosphere due to the absence of a strong magnetic field, which is influenced by the Sun. In summary, the Sun not only provides light and heat but also supplies vital elements for life. Moreover, its gravitational force shapes the dynamics of celestial bodies within the Solar System, affecting their orbits and atmospheric conditions. In addition, the Sun can also influence the orbital motion of asteroids, leading to the formation of meteor showers or asteroid impacts on Earth, which can have a significant impact on Earth's environment. Thirdly, the Sun is also an important subject of study for humanity in understanding the universe. The unique particle and magnetic environment of the Sun provide opportunities to study physical phenomena such as solar wind, cosmic radiation, and the imbalance created. The activities of the Sun also have an impact on Earth and other celestial bodies within the Solar System. Therefore, studying the Sun is crucial for gaining a deeper understanding of the formation and evolution of other celestial bodies within the Solar System. Lastly, the significance of the Sun in the universe is also reflected in its influence on cosmic rays. Solar wind consists of high-energy charged particles released by the Sun, and some of the solar wind will be reflected back by the external environment of the Solar System, forming cosmic rays. Researching cosmic rays is of great significance in understanding the processes of evolution, origin, and energy distribution in the universe.